everyone, my name is Angelica Giovanning, and today we will explore the importance of remote sensing and its application in monitoring coral reefs. What is remote sensing? Remote sensing involves gathering information about objects or areas remotely, typically through aircraft or satellites equipped with sensors that detect reflected energy from Earth. These sensors, which can be passive or active, capture natural energy emitted or reflected from the Earth's surface, with passive sensors commonly detecting reflected sunlight. In contrast, active sensors use internal stimuli such as laser beams to collect data by measuring the time it takes for reflected signals to return. This technology is crucial because it allows us to gather data on large and often inaccessible areas, providing insights that would be difficult or impossible to obtain otherwise. Coral reefs are among the most diverse and valuable ecosystems on Earth, yet they are under significant threat from climate change, pollution, and other human activities. Monitoring the health and changes in coral reefs is essential for their conservation and management. Remote sensing offers a powerful tool for observing coral reefs. By using satellites equipped with advanced sensors, we can monitor large reef areas, detect changes over time, and assess the impacts of environmental stressors. This data is invaluable for researchers, conservationists, and policymakers. The Advanced Land Observing Satellite, ALOS, launched by the Japan Aerospace Exploration Agency, provides high-resolution images and is particularly useful for detail mapping and monitoring of land and coastal areas. Its advanced optical and radar sensors can penetrate cloud cover, making it effective in various weather conditions. On the other hand, Sentinel, launched by the European Space Agency as part of the Copernicus program, offers a suite of satellites with different sensors designed for environmental monitoring. Sentinel-2 in particular provides multispectral imaging at a high spatial resolution, which is excellent for monitoring changes in coral reef health and extent. While both ALOS and Sentinel have unique strengths, Sentinel-2 is more commonly used for coral reef monitoring due to its high-resolution multispectral imaging and frequent revisit times. Coral reefs are among the most biodiverse ecosystems on our planet, teeming with life and beauty. However, they face numerous threats, including climate change-induced coral bleaching events. To monitor and protect these invaluable ecosystems, scientists have turned to satellite technology such as the Sentinel-2 satellite. However, this approach comes with its own set of challenges. Let's explore several major problems associated with using Sentinel-2 satellite for coral reef observation. Firstly, let's talk about data resolution and accuracy. Sentinel-2 satellites provide images with a spatial resolutions of 10 to 20 meters. While this is impressive, it's not always detailed enough for fine-scale coral reef studies. The lack of finer resolution can lead to inaccuracies in identifying and monitoring coral reefs. Next, cloud cover and atmospheric interference pose significant problems. Clouds and water turbidity can obscure the reefs, making it difficult to get clear and consistent images. This reduces the quality of data available for analysis. The effectiveness of satellite sensors like those on Sentinel-2 is limited to shallow waters. This means monitoring deeper coral reefs accurately is a challenge. That limitations restricts the full potentials of satellite data for comprehensive coral reef studies. Another issue is the integration with in-situ data. Integrating satellite data with in-situ observations is crucial for accuracy. Without concurrent field data, validating the satellite data becomes difficult. This integration is necessary but can be resource-intensive and complex. Now, let's examine how different parties are impacted by the challenges in satellite-based coral reef observation. For researchers and scientists, data quality and resolution are paramount. The limitation in these aspects directly affect their ability to conduct accurate and comprehensive coral reef research. Conservationists and environmental organizations play a crucial role in monitoring reef health and implementing conservation strategies. However, data issues such as poor quality or resolution can impede their efforts to protect these vital ecosystems. Policymakers and government agencies rely on reliable data to make informed decisions and plan effective marine conservation efforts. Inadequate data can lead to the formulation of ineffective policies, putting coral reefs at further risk. Finally, local communities and stakeholders. Coastal communities that depend on coral reefs for their livelihoods, such as those involved in fishing and tourism, are indirectly affected by the quality of satellite data used to monitor reef health. The accuracy of this data directly impacts their economic well-being and way of life.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Shafiqah and I will be explaining about the solutions as well as the study gap for these studies. First of all is the solution. The first solution is super resolution. Apply super resolution techniques to enhance the spatial resolution of Sentinel-2 imagery. These techniques utilize advanced algorithms to interpolate or extrapolate pixel information, effectively increasing the level of detail in the images beyond their native resolution. Second is atmospheric correction. Apply atmospheric correction techniques to satellite imagery to compensate for the effects of atmospheric interference, such as scattering and absorption of light. These corrections remove atmospheric artifacts and improve the accuracy of surface reflectance values, enhancing the quality of data for coral reef analysis. Next is bathymetric mapping. Conduct bathymetric surveys using sonar or LIDAR to map underwater topography and identify deep coral reef habitats. High-resolution bathymetric data provide detailed elevation information, allowing researchers to delineate reef structures and assess their distribution and extent. And finally, data sharing and collaboration. Foster collaboration between satellite remote sensing scientists and field researchers to facilitate data sharing and exchange of expertise, maximizing the synergistic benefits of integrating satellite into data. We'll be moving on to the study gap. The first is spatial resolution. Sentinel-2 offers a 10-meter spatial resolution, which is good, but not good enough to detect small-scale changes in coral health. We need finer detail to monitor these delicate environments for more accurately. Spectral resolution. While Sentinel-2 has multiple spectral bands, more sensitivity to specific coral health conditions is needed. Advanced algorithms can help make better use of the existing spectral data. Next is temporal resolution is another challenge. Sentinel-2 revisits the same location approximately every 5 days, but more frequent monitoring is crucial, especially during events like coral bleaching. And finally, bathymetric mapping or underwater topography is possible with Sentinel-2 in clear, shallow waters. However, accurate mapping in turbid or deeper waters remains difficult. Integrating data from acoustic or LIDAR sources could improve this.
Hi, Assalamualaikum. My name is Izan Nabila binti Abdul Halim. This slide I want to focus on the problem statement from coral bleaching when using Sentinel-2 to observe coral. Coral bleaching occurs when coral expel their symbiotic algae due to stress from high water temperature, leading to increased morbidity and mortality. Coral reefs are declining at an alarming rate due to the combined effects of global change and human pressure. To address this problem, it is necessary to leverage the capabilities of Sentinel satellite and develop solutions that utilize the available observation. Here are the suggestions of solutions to solve the problem. First, multi-temporal imagery and change analysis. This method improves detection accuracy by capturing the spectral signal of recovered or algae overground coral. The Sentinel-2 missions, with its 5-day revisit time and spatial resolution of 10 meters, is particularly well suited for multi-temporal analysis of coral reef. The second solution is radiometric normalization and depth variance indices. For radiometric normalization, this method helps mitigate different causes by varying atmospheric conditions and sensor calibration over time, and for depth invariance indices. This method linearizes the effect of depth on reflectance, allowing for a more accurate classification of benthic habitats regardless of water depth. The last solution is monitoring water temperature. When water temperature become too warm, coral expel the algae living in their tissues, causing the coral to turn completely white. This process is known as coral bleaching. The satellite's ability to remove variation in overlying water and other change in the bottom, such as microalgae blooms, help in the detection of bleaching event before coral recovery or algae overgrowth turns the area dark again. In conclusion, Sentinel-2 has become an invaluable tool for coral reef observation. They provide high-resolution imagery and data on sea surface temperature, enabling the early detection of coral bleaching events. However, some challenges arise, such as data resolution and accuracy, cloud cover and atmospheric interference, depth limitation, and integration with in-situ data. Despite this challenge, satellites play a crucial role in understanding and protecting coral reef.